Hello, class. This is Mr. Hart, and in this podcast, we want to finish up the Simple Machines chapter of our textbook. And we want to finish up by talking about a term called efficiency. Okay, so if you've ever seen like a postman deliver a bunch of boxes to someone's door, they'll usually use one of these machines called a dolly. Okay, and if you've ever noticed, it doesn't take much effort on their part to push this dolly. Okay, and if you think about it, compare that to what they would have to do without the dolly, right? They'd have to lift each one of these boxes. Okay, take it to the doorstep or lift all three at the same time and put it on the doorstep. Okay, that wouldn't be a lot of fun for the postman, right? And so this dolly makes a lot less effort on their part. Okay, so we want to describe this, effort that they have to do in terms of what we call efficiency. Okay, or in other words, we want to compare what would they'd have to do without the machine compared to what they'd have to do with the machine. Okay, and so the efficiency, or in other words, what we call the mechanical advantage, which I'll represent with MA, okay, that's going to be equal to the force they have to put on the object without the machine, okay, that they're using, the dolly or the pulley or the lever or whatever it is, right? So it's the amount of force they'd have to put without the machine compared to the amount of force that they'd have to use with the machine. Okay, so it's the force without compared to the force with the machine. Okay. So without this machine, he'd have to use a lot more force, right? Because he'd have to pick up all three boxes by himself, right, and move them to the doorstep. Whereas with the machine, he has to use a lot less force. So he might need to use 8 times more force without the machine than with the machine. So his efficiency or his mechanical advantage is 8, okay? So let's look at some specific machines and see how we can calculate the mechanical advantage, okay? So let's start with a lever. So for example, with a lever, if we want to find the mechanical advantage, we can write it like this. The mechanical advantage is equal to the length of side 1, or the length of the side with the force on it, compared to the length of side 2. Okay, so that's the side with the load on it. So for example, if you're using a crowbar for example, prying up wood or tile or whatever it is, okay, you want a nice and long crowbar. Okay, because that's the length of side 1. You put the force on this side of the crowbar to lift up the load. So if this side over here is 3 meters long, and this side over here is only 1 meter long, then your mechanical advantage is going to be 3 over 1. Okay, or in other words, you'd have to do 3 times as much force, or put 3 times as much force without the lever compared to with the lever. Okay, another way you can think about it is you can flip that and say, I have to use 1/3 the force I usually would. Okay, and so if you think about a crowbar, this is an exaggeration. 3 meters to 1 meter, it's maybe a few centimeters. Maybe it's 0.05 meters, and this is maybe 2 meters long or whatever it is. Okay, in that case, you're going to have a very high mechanical advantage, right? It's going to be 2 over 0.05. If you simplify that out, you're talking about 40 times more force you'd have to use without the lever, right? So you're using 1/40th the force that you would use without the crowbar, right? So this is very useful, right? Your mechanical advantage, you want to be as high as possible because that means you have to use a lot less force, okay? And so that's why simple machines are so useful, because it's decreasing the amount of force you have to do. But again, what's the trade-off? You have to use more distance, right? You have to move the crowbar a lot farther compared to the without using the crowbar. Okay, but again, mechanical advantage of a lever: length of side 1 compared to length of side 2. Okay, what if it's not a first-class lever like this, though? What if it's a second-class lever where you got the load in the center, you got the force right here, and you got the fulcrum on this side? Okay, can you still use this equation to calculate the mechanical advantage? Well, you can. You just have to count length of side 2 as just this distance to the load. Okay, so that would be side 2. And then side 1 would be this distance to the force itself. Okay, so you can still use the same equation. It's just that the sides are both on the same side. Okay, and so you just have to think which one's to the force, which one's to the load. Okay. Excuse me. All right. So for any lever, we can figure out how much less force we have to use by calculating the mechanical advantage. Okay. We can also find the mechanical advantage of a pulley. Okay, so the mechanical advantage for a pulley is equal to 2n. Okay, and n is the number of movable pulleys in a system. Okay, so look at this complex pulley here. Okay, we have some fixed pulleys, we have some movable pulleys. Okay, and they're moving back and forth, moving back and forth. Okay, if you look at this picture, you'll notice that if I pull down on the rope, right, pull down on the pulley, apply a force, okay, not only am I lifting the load down here, but I have to lift this pulley, I have to lift this pulley, I have to lift this pulley, and I have to lift this pulley, okay? And so all 4 of these movable pulleys have to be lifted as well, okay? So I'm going to have to pull 8 times as much rope, okay? But that also means that the amount of force I'm going to have to use is 8 times less, okay? Because now instead of having to lift the whole load by myself, I have 4 movable pulleys to help me, okay? They're going to take a lot of the effort away. Okay, so the mechanical advantage, 2n, if I count how many movable pulleys I have, 1, 2, 3, 4, my mechanical advantage is going to be 4 times 2, which is 8. Okay, and so I have to use 8 times as much rope, but I have to use an eighth as much force. Okay, and if you think about it, that makes sense because there's 1, 2, 3, 4, 5, 6, 7, 8 ropes that are helping me pull up this load. Okay, so those 8 ropes are going to make it so I only have to use an eighth as much force, but it also means I'm going to have to pull 8 times as much rope. Okay, so again, it doesn't matter how many fixed pulleys you have. You could have 100 fixed pulleys. It's not going to do anything. Okay, it's just going to change the direction. How many movable pulleys you have, though, that's what's going to help you lift something up. Okay. So mechanical advantage equal to 2 times the number of movable pulleys. Okay? All right. And the last one we want to be able to calculate the mechanical advantage for is for an inclined plane. And this one's really simple. The mechanical advantage is just equal to the length of the incline compared to the height of the incline. Okay? So for example, along this ramp, if I move along the ramp, it's a total of 4 meters long, and the height of the ramp is 2 meters. So compared to the ramp, I have to push it twice as far, right? 4 meters compared to 2 meters, right? Or in other words, it's 4 over 2. So my efficiency, or my mechanical advantage, is equal to 2. Okay, and if you think about it, it makes sense. I have to move it twice as much distance, right? But I only have to use half the force. Okay, so I'd have to push with half as much force to get up to that location. So this also explains why you want very shallow inclines. Okay, you want to make this length of incline very large compared to the height of the incline. The larger the length of the incline, the more efficient it's going to be. Okay, so you want something that's nice and long and shallow like this. Okay, so you have a very long incline compared to a very little height compared to something that's nice and steep where the height and the length are pretty much the same thing. This is not a good situation. This is much better because the length of the incline is much larger compared to the height of the incline. Okay, so the larger that length, or basically the shallower the angle, okay, the more efficient that incline plane is going to be. Okay, but again, the trade-off is you have to push it farther, but you can use less force. All right, so those are the 3 we'll look at. Okay, levers, pulleys, and inclined planes. You can figure it out for screws and wheels and axles and for wedges, but we won't worry about it for this class. Okay, let's look at an application of some people that really understood this idea. Okay, the ancient Egyptians, when they built the pyramids. If you look at how they built the pyramids and some of the historical findings, you'll understand that they knew simple machines very well. Okay, they understood inclined planes, they understood pulleys, okay, they understood wheels and axles, and they knew how mechanical advantage worked. Okay, they may have not called it the same thing, but they understood the shallower the inclined plane, the easier it is to pull it up. Okay, the more lever systems you use, the easier it is to pull the object up. Okay, and so they obviously understood these principles. Okay, a couple more terms we want to look at. You'll hear a term called ideal efficiency and a term called actual efficiency. The ideal efficiency is what we actually have been calculating here. Okay, in these couple of examples, that's the ideal mechanical advantage. Okay. In the real world, because there's things like friction and air resistance, okay, and some of your energy is lost to heat, you're not going to get exactly what you calculated. You're going to get what you call the actual efficiency, or what it actually turns out to be in the real world. Okay, so you may use a lever and you calculate that the efficiency should be 2, but in the real world, it's only 1.8. Okay, doesn't mean you did the calculation wrong. It just means that there was other things that came into play, like again, friction and air resistance, or maybe the lever wasn't exactly rotating perfectly around the fulcrum, or whatever it may be, right? There's other things that come into effect. So that's our actual efficiency. Okay. So just understand what you calculate, your ideal efficiency, and what you actually get won't be the same thing. Okay. And then there's one last term we want to talk about, and that's a compound machine. And that's just a combination of two more simple machines. Okay, for example, a wheel and axle, which can be combined to a lever to make a wheelbarrow, right? You want to move the material up, but you also want to move it sideways. So you combine the two and you get a wheelbarrow, okay? Other examples of compound machines are bicycles. There's pulleys, right, for the chains. There's the wheel and axle. The handlebars are a lever, okay? A lot of things in the bicycle make this a compound machine. Okay, a can opener has 2 levers on it. It has a wheel and axle. It has a wedge that actually, bite into the can. Okay, a sewing machine has a wheel and axle for the thread. It has a wheel and axle to rotate. It uses a lever to push on the machine to make it move. It has a wedge in the needle that gets it to go through the fabric. Okay, and so on. So by combining a bunch of simple machines together, we can make much more complex machines that we can still use to make work easier, okay? And so a lot of the mechanical advantages are combined together when you make a compound machine, okay? Alrighty, so in this podcast, we looked at how to calculate mechanical advantages for a bunch of simple machines, and we looked at how to make a compound machine, okay? Hopefully that all makes sense. Let me know if you have any questions, and thank you for watching.